Last time I did a video on my own Hexapod robot, I showed my design process for a first prototype. The robot could not stand up by itself, but hold its position when lifted in place. The new version shown in this video will be completely redesigned to allow for better performance. This version contains several large topics that I don't want to cover in one stretched out video, but in several smaller ones. This video will include the following topics: the mechanical redesign, the electrical redesign, assembly, and some test programs. With this overview in mind, let's first go over the requirements next. The requirements for this video are the following. The result from the previous version will be based on during this version. You might watch the video for that before continuing this one to get the required context. As last time, if you want to replicate this robot, you will need a basic understanding of electronics and how to establish electrical connections, as well as a bit of programming. The programming for this version is pretty basic, but this will change in the further development. More on that later. And as last time too, I will use my 3D printer to create the parts required for the new body. With that out of the way, let's get going with the design changes. The design from the last version was flawed in several points, for example the overall size in regards to the servo motors, or the insufficient power supply for the electronics. Let me show you what I changed. Before designing the new body for the robot, I first did some more research on the internet for other people who have built this kind of hexapods. I actually found this video here from Small Pete Sai, who has built a very good hexapod. I took inspiration in his design, which is very much present in my own design. The first concept for the design is to arrange the electronics. In the last version, the electronics were stretched out over the complete body. The length of it gave me enough room to fit everything, but in this version I wanted it to be way more compact. In order to achieve this, I determined the largest part and placed this at the center of the body. This will also help in the overall balance of the robot, because the main weight is now in the center. I then determined all electronics that I need and want to have. While the microcontroller and one of the two PWM boards from the previous version are known, there are some new parts. The first new part is an MPU 6050 inertial measurement unit. This device will provide me the data regarding orientation and accelerations that I want to use at some point in the program. The next new parts are Mini 360 step-down converter mounted on a PCB. Each of these can output up to 2 amps at 5 volts. This means that I have 2 amps available for 6 servo motors. In comparison, the previous version had 2 amps for all 18 servo motors. The last parts are of course the servo motors, but these will be added together with the legs. I deliberately first chose the electronics to get an overview of how much space I need to fit everything on the robot. This led me to the second step to the design process. Arrange all components so that they require the least amount of space. I tried several combinations but eventually landed on this configuration here. The battery is in the center of the robot and the electronics are arranged on top of it. From this, you can already somewhat guess the shape of the robot. With the arrangement completed, the next step is to design the torso to hold everything together. Here you can see the result, which is quite different from the first version. Instead of long and solid parts, the torso is constructed with a skeleton-type structure. This minimizes weight while still being rigid. Here you can also see where the legs will be mounted. As in the reference, I angled the front and back legs at 45 degrees away from the center legs. This gives me some movement area while minimizing the size of the torso. The legs start with a small mount for the servo and connect to the next leg part by a connector piece. This assembly is the hip of the leg. The next part is pretty much taken directly from the last version, because there wasn't much to change except the length of the part. This version is now limited by the size of the servo motors. The connection between the hip and this part is the knee of the leg. The last part is the foot of the leg. This has changed quite a bit from the previous version. Instead of a curved part, this is now straight and has minimized weight. These are all required parts for the robot, so when you combine everything together for all legs, you get this assembly. Looks quite different from the last one. Regarding the software, not much has changed from last time, at least in this video. This is why you might refer back to the previous video in case you want to know what was covered there. The software now includes 2 new functions to stand up and sit down. Both are done by going step by step through hard-coded positions at hard-coded intervals. I did this on purpose because eventually standing up and sitting down will be possible by using the inverse kinematic model. This version actually currently does not have one, it is still in development. This means that in contrast to last time, the inverse kinematics will not be covered here. This is the overview for the main design changes and a part of the software changes. Let's continue with building the new robot. As I said in the introduction, I used my 3D printer to print all parts for the new robot. The amount of parts went down compared to last time, because I already had a lot of dimensions right from last time. I first started with the mechanical assembly. For this, I needed to gut the parts from the old version. Here you can see a direct comparison in size. The previous version is much larger than the new version and has a lot more material to it. Here you can see all parts for the robot. I already tested around with one leg and some electrical components to make sure everything fits. After putting everything together, the robot already looks much better. The next step is to solder the step-down converter onto the PCB. You can see the layout on the top here and the solder connections on the back here. The power from the battery is provided via the screw terminal on the left, and all other components get their power from the array of pins on the bottom. The last step is to wire up everything. Here I first needed to get an overview over all the individual cables, because there are quite a lot. You can see the wiring diagram here. As you can see, the main portion of the cables are from the servo motors. Next I mapped out how many connectors I need for all wires, like you can see here with the empty connectors on the pins. I then proceeded to first connect the power cables, as visible here with red and black wires. After that, the I2C cables were added as blue and green cables. Here you can also already see that I used the spacing between the torso and the electrical components to guide and hide the wires. This way the whole cabling turned out pretty neatly. The last part was then to remove the connectors from the servo motor cables and put on new ones for the new wiring. These were then managed through the gaps of the torso and finally connected to their destination. The result is a neatly cable managed robot. I actually tested here if it could already stand, and indeed it could hold its position without any set position for the servo motors. These were actually not even driven, so they had no holding torque except the friction in the joints. As I said earlier, the software didn't change much except the mapping of the servo motors on the PWM board. The stand-up procedure is achieved by first moving the knees up, then the feet down, and then the hips back down. This will be shown shortly. With the robot finished and ready to go, let's do some tests. The first test was to calibrate the servo motors. As the procedure is identical to the last video, I will skip over this. One change was in the definition of the coordinate systems of all joints. This is also a step required for the inverse kinematics, which will not be covered in this video. Following the procedure from last time, the next step is to stand up and newly to sit down. As you can see, the robot first moves the knees up, then the feet down, and finally the knees back down. The result is a somewhat 90-degree angle between the legs and the feet. To sit down, the procedure is simply inverted. You might have noticed that one of the feet twitches at some point. This is due to an error in the calibration that will be fixed next time. I also did another test where I wanted to find out how much weight the joints are able to hold. For this, I actually stacked some cable rolls on the robot and it could hold them without any problem. I could also significantly press down on the torso and the robot could carry the extra load. These were actually all tests that I want to cover for now. I will do more tests in future videos with this version, but more on that after I conclude what was achieved in this video. This version of the Hexapod was really successful and has a lot of improvement compared to the previous version. The complete redesign of the body resulted in smaller body size and lighter weight. The updated power supply provides 3 times the current to the motors, effectively tripling the available power of the robot compared to the previous version. A first test shows that the robot is able to stand up by itself. A next test shows that the robot is even capable of carrying some amount of weight. The price of this version of the robot didn't really change to the previous version, only increasing by about €2 to a total of €88. This was achieved by the weight savings of the prints and by removing or swapping out some electronics. I'm really glad how this version turned out, and I have quite some tasks planned for it. First I want to implement an inverse kinematic model. Here I want to use proper notation that is used in robotics called Denavit and Hartenberg notation. If that does not work, I will fall back to the same style of inverse kinematics I did on the previous version. This is actually already on its way since April 2022. The next immediate plan is to remote control the robot. This is also already in progress since May 2022. From here on out, the goals are defined more broadly. The overall goal is still to have a robot that can move according to inverse kinematics. This also includes taking steps and moving generally freely in 3D space. I probably will do some more complex stuff when all mentioned goals are achieved. Similar to the previous version, this project actually started in February 2022, but is still ongoing. The main reason for this is that my focus shifted slightly, as you might be able to tell from all previous videos on this channel. Anyway, I will continue to work on this project in the near future, because I really want this thing to work. This was the last video for my sudden grind for uploading videos, so expect the next one in my usual tempo, meaning probably in 6 months or something like that. If you watched the last few videos, you might know that I have quite some work to do. Thank you as always for watching and see you in the next one. As a small taste for what is to come, here's a peek into the world of inverse kinematics.